not.
And the other one is the Copenhagen interpretation. So where do we get those interpretations from?
You're watching a Nova Video podcast.
Like that, moving around.
Particles dissolving into waves. Waves of what?
It's
All right, guys, this is Bose-Einstein condensate. State of matter near absolute zero. Particles will dissolve into waves. Waves of
really
what?
difficult for me to explain just why that is, but that's the way it is. They're everywhere. This little wave packet over here can't tell it whether it's this one or that one or that one or that one or that one.
And then the particles will start to appear at multiple locations.
It's there. Running around gaily, freely bouncing into things, sometimes going fast, sometimes going. There's nothing else like that in physics, and certainly not in human experience. So just to think about M anymore, I'm at rest, and all the other atoms gaily, freely bouncing into things.
And then near absolute zero, the atoms will slow down.
Sometimes going fast, sometimes going slow. But on the Bose condensate,
and then next thing you know, the same atoms will appear at multiple locations.
Everywhere at once. I've lost my identity. I don't know who I am anymore.
And there's also a statement in the documentary that says absolute zero could never be reached because the last bit of energy would take forever to remove from that system. So why is it that when the atoms start to slow down, they will appear at multiple locations? Where do we get that understanding from? And why is it that the physicists are so certain that you could never reach absolute zero? Because the last bit of energy would take forever to remove from the system. All right, guys, take a break for 10, and then we'll take it from here. And let's see. Okay, so going back to the same question. Light, composed of particles or waves? Newton said it was composed of particles, and Huygens said it was composed of waves. Initially, we decided that Huygens was correct. What do we know today? Today, we know that it's both, right? Depending upon the experiment, it can act like waves or it can act like particles. So the question was, and this is something that Einstein was thinking in 1917 or 18 when ST was working on his theory of gravity. I was thinking that, can we make the same argument regarding these particles? I mean, electron, no one has seen an electron before. So can we make the argument that the electrons may also have a dual nature? About atoms, about molecules. Is it possible? He was thinking about it on the side, but he didn't really put anything on paper. About at the same time, this guy in the background was thinking about the same thing. All right, so this is the guy. What's his name? All right, in the United States, depending upon who your professor is, his name is either de Broglie, and you pronounce everything in sight, pronounce the shit out of everything, or acknowledging that this guy is French, you may go, okay, so I know there's some silent letters here and there, but you don't know which ones because you're not French. Only the French know which ones. French usually put half of their alphabet in every single word, and they're the only ones who know which ones to skip. All right, so you would say de Broglie. All right, so that's a bit of an acknowledgement that this is French. And who would have guessed that his name is de Broglie? All right, so that's French for you. Weirdos. All right, so this guy is working on his PhD dissertation, and is pondering about the same question. Is it possible that these particles also have a dual nature? Is it possible that they can act like waves? These particles can also act like waves.
A century earlier, Thomas Young had proved light travels in waves. Was it now going to turn out that light is really made of particles after all? Perhaps this whole business of particles and waves was in need of an entirely fresh perspective. Louis de Broglie got a history degree en route to a career in French government, a fresh approach to physics if there ever was one. Maybe that's why, in the 1920s, he was the one to ask a crucial question. If light waves can be particles, is it possible that particles, such as electrons, can also be waves?
All right, so let's talk about his background a little bit. Number one, this guy is a prince. And if you ever wonder why all the royalty look alike in Europe, because they are related, they're like family members. They are like family members. Most of them are cousins, distant cousins. And for whatever reason, most of them have horse faces. I don't know why. So this guy is royalty. He's got a background not in physics. His background is exactly the same as Ed Witten's background. History. It's got history or anything to do with physics. Nothing. This guy's an outsider. So he's pondering. Is it possible that given the fact that light has a dual nature, can we make the same argument regarding particles? Is it possible that they also have a dual nature? Particles, could they have a wave nature as well? This is the sort of stuff that only an outsider can ask, because no physicist would take something like this seriously. So this is his doctoral dissertation. They've been working on it for 2 years. And then he's about to publish it and defend it. And that's the question that he's trying to resolve. All right. Take a look at the first equation up. Okay. You got the wavelength on the right, Planck's constant, divided by P. This P is known as momentum. This is my fourth tempo moving at 60 miles per hour. You got your speed, and you got the mass. And P is known as momentum. Momentum is an ordered way of saying motion in a given direction. What is it that I'm looking at and not liking? Everything. Everything is bullshit. I look at it, I say, holy shit, I can't believe this guy actually got away with this for 2 years. And I just feel like I want to kill someone. And I have to listen to this guy talk French. He said, blah, 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 blah. I just want to grab him and then squeeze the shit out of him. I want to kill this guy at this point because he's about to waste my time. I'm really angry with his advisor for letting him get away with this bullshit. What's the problem that's really pissing me off? Wavelength means that there's a wave associated with the motion of my fucking four tempo. There's no such thing. Wave of what? This is my four tempo moving at 60 miles per hour. It's creating waves. Waves of what? There's no such thing. There is no such thing. At that point, I would just put a stop to it. I would say, what is this? What is this the wave of? It's going to say, oh, blah, 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 blah. This is your four tempo moving at this spell. Just shut the fuck up. All right? You can't explain it. And that immediately gets into trouble. Immediately. This guy opens his mouth. At that point, he's in deep water. He's not going anywhere at this point. All right? He's a fair game at this point. You skin this guy alive. This is complete fucking nonsense. At that point, it's just a game ender. Because you can't explain this. Wave of what? This is literally a mass moving at this speed. Would not generate waves. There's no such thing in physics. Complete nonsense. Who else knows that this is complete nonsense? His advisor does. His advisor does, because what this guy did, he takes Einstein's equation up, mc squared, and combines it with the photoelectric effect. And somehow, through mathematical manipulation, I don't know why it takes him 2 years, he comes up with this. That's not how physics is done. These symbols mean something. You don't just play with the symbols and come up with an equation and say, this is my PhD dissertation. Only a guy who's not a physicist would do something this stupid. So his advisor sends the advanced copy to Einstein. Einstein looks at it. He says, oh, you guys are French. You wouldn't be able to get this. And De Broglie is correct. So just give him his PhD. Next time when I'm in France, I'll explain it to you guys. If Einstein is in agreement with you, obviously you don't question it. So the PhD board are really pissed. But they say, hey, Einstein likes it, so we're not going to question it. Why did you come up with it? What are you thinking? What's your understanding of it? Because this explanation is complete bullshit. All right, this explanation does not work. He was never able to explain this shit. He says, oh, here's what I'm thinking. Remember the standing wave patterns? Both ends are fixed. And remember the fact that no one knew how to explain the Bohr's orbitals, where these orbitals come from. He says the electrons, by their motion, they create these matter waves. He says, I don't know what these matter waves, but the motion of the electrons, the momentum, mass, and the speed generates these matter waves at locations around the nucleus, where the matter waves form these perfectly circular orbitals. That's where the orbitals will happen. Guess what? When you plug the numbers in, damn, you end up getting Bohr's orbitals. And all of a sudden, assuming that the electrons generate these matter waves and at locations around the nucleus, these orbitals form perfectly circular standing wave patterns. That's where the orbitals are. Beautiful. Now it works out. Now everyone is interested. No one gets the idea behind it, but the electrons, by their motions, generate these matter waves at locations around the nucleus where they form these perfectly circular orbitals. That's where the orbitals are. All right, so this is Einstein saying, hey, just go easy on him. As far as he was concerned, De Broglie's theory was correct. He said, you guys won't get it, but I'll explain it later. So Einstein put his support 100% behind it. So the next question is, how do we know the existence of these matter waves? How can we test for them? Well, how do you test for the existence of waves? Remember the double slit experiment, all right? You will have to look for an interference pattern. So he said, if you get the electrons to move roughly about 10 million miles per hour, all right, they would generate these waves. Those wavelengths would be comparable to the wavelengths of light going through a double slit. So which means that you would see some kind of an interference pattern. All right, the spacing between the atoms is comparable to the wavelengths of these matter waves. So by using spacing between the atoms, they end up using this metal foil, and then they send these electrons through them. Okay, the X-rays that you're looking at, fast-moving electrons, and then sure enough, it causes these interference patterns on the wall, on the screen. All right, so this is the electron diffraction pattern, the interference pattern. This is the X-ray diffraction pattern. Notice that the electrons end up causing a diffraction pattern, which is much clearer, much higher resolution than that. The guy who ended up doing the experiment, his name is George Thomson. Ends up winning the Nobel Prize in 1937 for proving that the electrons also have a wave nature, because the electron matter waves also interfere, just like light does. It happens to be the son of J.J. Thomson, who discovered the electron. So J.J. Thomson ends up winning the Nobel Prize in 1906 for proving that electron is a particle. In 1937, his son wins the Nobel Prize for proving that the electron also has a wave nature. Same family, 2 Nobel Prizes, and same topic, the electron. So what does it mean? So not only de Broglie gets his PhD, also wins the 1929 Nobel Prize for discovering the matter waves. So what are these matter waves? We discussed that. The only thing I'm going to say is electron microscopes do use matter waves, and by using matter waves, look at the resolution. This is macro, guys. Look at the resolution. Unbelievable. By using the wave nature of electrons, which happens to be known as the matter wave of the electrons, you can come up with the resolutions which are unbelievable.